Good morning. Today, I want to make a few more comments before we get started on the last part of the development of our ideas about the general theory of relativity. I'm still thinking of the situation of dust as my motivation here. We will change that later. Previously, we had decided that conservation of energy, conservation of mass as well, was represented by the divergence of the flux of energy or matter across surfaces of different constant coordinate values. In terms of our new language, the conservation law for energy, we'll just call it, is T0 nu differentiated with respect to nu and summed on nu. This is the divergence of the T0 component. If energy is conserved at a point, then that divergence must be zero. On the other hand, as we've previously seen, exactly the same logic can be applied to any quantity that each particle carries. So there should be a similar thing for the x component of the 4 momentum, the y component, and the z component. These three equations, after the first one, represent conservation of 4 momentum in the x direction, in the y direction, and in the z direction. But if you look at those 4 equations altogether, they're the same except for the first index on the t tensor. I can summarize this by writing t mu nu, comma nu equals 0, with the understanding that the nu is an index of summation and that equation is supposed to be true for mu equal 0, 1, 2, and 3. If you're in a flat space-time and are using flat coordinates, then the partial derivatives of tensor components form new tensor components. However, if you're in a flat space-time and using curved coordinates, that's no longer the case, but after a great deal of discussion previously, we have figured out how to fix that. This, for instance, would allow you to use spherical coordinates for the space part, if you like. This same formula holds true in a curved space-time by doing the usual procedure. At a given point that you're interested in, set up a locally flat coordinate system. This equation is true at the point at which you set that system up. However, covariant differentiation does give you tensor components back. So this equation is a tensor equation that's true at the point of interest in terms of the locally flat coordinate system at that point. This equation is true at a given point in one coordinate system, and since it's a tensor equation, it's true in all coordinate systems at that point. We didn't say anything special about which point we were talking about, so we can say that this is a general expression of conservation of 4 momentum, even if you're in a curved space-time. Because of the resemblance to the three-dimensional divergence of a vector, any tensor T that obeys such a restriction is said to be divergence-free. The Newtonian field equation for the potential of a gravitational field is the Laplacian of the potential equals 4 times pi times Newton's constant of gravitation times the mass density. I'm using kappa for the gravitational constant because there's going to be an awful lot of things named G coming up, and I just want to keep the confusion down. Thinking of being in the rest frame of dust, or in a frame that moves very slowly compared to that frame, the mass density as measured in the rest frame is the 0, component of this stress energy tensor. I want to begin thinking about this so that I can begin making some mental guesses about what the other side of the field equations are going to look like. Referring back to the toy problem, the only component of the metric that was of any significant difference from Minkowski was the 0, component. It worked out to be the negative of 1 plus 2 times the gravitational potential. If you calculate the Laplacian of this, you'll find out that the Laplacian of G00 in the downstairs position must be 2 times the Laplacian of the gravitational potential, which of course means that the gravitational potential is 1/2 Laplacian G00. Combining these facts, the dust begins to settle, if you'll pardon the expression. The Laplacian of the interesting component of the metric is 8 times pi times Newton's constant times the 0, component of the stress energy tensor, which in the rest frame, or a frame moving slowly with respect to it, is the mass density. We're beginning to see the outlines of what's going to happen. On this side of the equation, we will have, besides mass density, energy density, we will have any fluxes of momentum across various surfaces. We will have to consider all of the components of the T tensor. In the simplest possible case, this will reduce down into the Laplacian of the interesting component of the metric tensor. A purist might make an objection at this stage. These indexes are in the upstairs position. These are in the downstairs position. On the face of it, this equation doesn't make any sense. However, we're working in the weak field case and in the toy problem case in a situation where the metric is very nearly Minkowski. It turns out that this isn't a big problem. We're looking at the simple case in the weak field approximation of the toy problem. G00, with its indexes in the downstairs position, is the negative of 1 plus 2 times the potential. On the other hand, the metric in the toy problem is diagonal. The entry G00 in the upstairs is just the entry in position 00 of the inverse matrix to these. Since the matrix is diagonal, this will just be the reciprocal of G with zeros downstairs. On the other hand, I'm thinking of the U as being small, so I can expand 1 over 1 plus 2u in a geometric series and only keep the first 2 terms. Then the Laplacian of G00 with the zeros in the upstairs position is the Laplacian of -1 times the Laplacian of -2u. That would be Laplacian of 2u. Factor the 1/2 over to the other side. My field equation turns back into Laplacian G00 upstairs equals 8 pi Newton's constant times the 0, component of the stress energy tensor. To do the Laplacian, which in our previous work had absolutely nothing to do with gravity at all, we figured out that we needed to take the partial derivatives of the potential with respect to coordinates. They gave us components of one forms. The index was down. To get the index in the up position, what we had to do was we had to raise the I that was downstairs on the U until it's upstairs. We had to do a tensor raising or lowering operation. After that, we have to take the covariant derivative of that. These GIJs with the indexes upstairs are just complicated algebraic rearrangements of the G mu nu indexes downstairs. But it gets worse than that. I'm going to multiply these things by derivatives of metric tensor components in the downstairs version with respect to various coordinates. I'm taking some of the things that I'm interested in and multiplying them together. The quantity inside the bracket will be the sum of many such things. Then, when I do the covariant derivative, even if I'm close to doing a Minkowski type space, the derivatives of everything that's in here will show up. So what you're going to get is some awful sum of quantities that involve components of the metric, partial derivative of those, second partial derivatives of those, and to make matters worse, a lot of these things are going to be multiplied together. The Laplacian of U from the Newtonian theory is going to become some enormously messy thing involving nonlinear combinations of metric tensor and metric tensor first and second derivative components. It's going to be a mess. One last time, in the simple toy problem, the field equation looks like Laplacian of G00 in the upstairs position is 8 times pi times Newton's constant times T00, with zeros now in the up position to match the other one. Einstein's thought was this. This is one component of a tensor equation. When you account for all fluxes of energy and momentum, you're going to have to look at all of the components of the T-tensor. Einstein proposed that the proper gravitational field equations for general relativity should be a tensor equation. The right-hand side of the equation should be 8 times pi times Newton's constant times the components of the stress energy tensor. The other side of the equation must be a tensor also. We're going to make up a name for this tensor. We're going to call it capital G. The field equations will be capital G mu nu equal 8 times pi times Newton's constant times the mu nu component of the stress energy tensor. We have achieved less than you might think because we know very little about this capital G tensor, although we do know certain things. Strictly speaking, we've only convinced ourselves that the T-tensor is symmetric in the case of dust, but it turns out to be true in general. T mu nu equals T nu mu because G mu nu is a constant times T mu nu. The Einstein tensor needs to be symmetric as well. Secondly, the Einstein tensor must be divergence-free. That is to say, G mu nu semicolon nu must be 0. The reason for that is this quantity is a constant times T mu nu semicolon nu, and conservation of momentum says these numbers are all 0, so these numbers must all be 0. In an effort to retain as much similarity as can be with the Newtonian theory, Einstein hypothesized that the components of this tensor we're looking for is some sort of monstrous combination of metric tensor components, their first partial derivatives, and their second partial derivatives. It's going to turn out that just given these assumptions, this pretty much nails down what the Einstein tensor has to be. It's going to turn out that except for one adjustable parameter, this is going to completely specify what the Einstein tensor is going to be. From a mathematical point of view, we are now suddenly extremely interested in how things like components of the metric, their derivatives, their second derivatives, can be combined and used to describe things that eventually will settle down in the limit to be the Laplacian of components. This is the clue that Einstein picked up on in order to develop the G tensor. In the next video, we're going to begin looking really hard at what distinguishes a flat spacetime from a not flat spacetime, and this will give us the wedge in to finding the Einstein tensor. In the meantime, I hope everybody's having a good day, and I'll talk to you again soon.